Okay. Hi everyone. I think we will make a start. So last week we started talking about matrices and about linear algebra. So today we're going to continue on this with this material. Before I go any further, so we will actually repeat some of the stuff we said last time, and then we'll go on a bit more. So we also said, may I remind you that next week, for the second, maybe for 40 minutes or something, we will actually go through an exam type question. I'm going to send you kind of a handout on Monday, hopefully, right? So in any case, before next Thursday, so you can actually have the chance to have a look. And then I would expect you to come here and have pen and paper with you, so it's not going to be particularly electronic, what we'll do, because in any case, the exam is just a written exam, right? So we need to make sure that we can deal with this, okay? Also last week, I understand you did the first quiz, right? Do you have any questions about the quiz? Or any questions since last time that you would like to ask? Okay. Okay, so let me just start then. So what I'll try to do is that I'll try to cover all the slides that you will have in two PowerPoint presentations over the course of the 3 lectures. So hopefully you can actually navigate yourself in this material. Okay, so we said that matrices can be seen as linear maps or linear transformations. So we said that vectors can be seen as representing points in space. Vectors will have 2 or more elements. They're usually, they can be multidimensional, obviously. And so then we can actually see matrices representing linear transformations, that is the translation of a vector of a point, this point, into a different space, into a different vector space, or into a different place inside the same vector space. And we said that vector spaces are just these abstractions where vectors live. So vector spaces define things like the dimensionality. For example, is it a 3-dimensional vector, a 5-dimensional vector, a 1,000-dimensional vector? And also certain operations have to be able to happen within that space, right? So if you, for example, add 2 5-dimensional vectors together, you're expecting to get a 5-dimensional vector, right? Okay, right, and what is a linear transformation? A linear map is basically a function that will actually take you to another space, to another place. We will actually transfer a point into a different space in a kind of predictable and simple, fairly simple way. So we also said that we can do a number of things with matrices. We can add or subtract matrices, right? We can scale them using scalars. Just numbers that will actually grow or shrink their elements. We can transpose them, that is, we can exchange rows with columns inside matrices. We can apply them to vectors, as we said, so that we can transform the vectors, that is the point in space, and we can also multiply them together, right? And by multiplying matrices together, we're effectively composing a new effect, we are creating a new effect by combining the effects of the two constituent matrices. Okay, so this is how we write matrices. These are the elements. Okay, so linearity. I'm revisiting these issues because they're really crucial for us. So what do we mean by linear transformation? Again, very specifically, we mean that if we transform the addition, the sum of two vectors, then this is the sum of the transformation of the two vectors, right? Which is that if I have this operation here, where A is a matrix and X and Y are vectors, I'm expecting to get this result. Okay. And also the transform of a scalar multiple of a vector, that is this one, right, is the same as the scalar multiple of the transform, right? Is that clear? We can have different maps and different mappings and different transformations that maybe do not adhere to these rules, but these are not linear then, right? Okay, so here it also says anything which is linear is easy. Anything which is not linear is harder. Right? Okay. And so a linear map is any function that satisfies this linearity requirement, the two requirements, I'm saying. Okay. Okay, so if the map has the property A times X is A times X, that is basically you apply the matrix operation twice on itself, then this is called the linear projection. So in this case, it doesn't matter how many times we apply the transformation of a matrix to the vector. Okay, so then let's see again a few examples of linear transformation. So the transformations that we're talking about are really the rotation and the scaling of the vectors. And here we have 4 points where A is the origin in that particular case. So we can actually, if we multiply a vector by the identity matrix, which is this one here, is 1, 0, 0, 1. So it has ones in the main diagonal, then basically we don't get any transformation at all, effectively, right? So the original vectors remain the same. If the main diagonal is a number less than 1, then we are basically just shrink the vector. And if the anti-diagonal are zeros, then we're not really rotating again, right? So we're just scaling, right? And the equivalent happens if you want to enlarge it, to enlarge the vector. If you want to, for example, to change like to scale one of the dimensions, then you need to have sort of the diagonal has to have different numbers, right? So here the 0, 5, 0, 0, 1 will actually shrink one of the dimensions, right? This is a rotation here. So we basically rotate all the points A, B, C, and D according to this by 90 degrees. So you see that point A comes up here, right? And the whole shape gets rotated, right, by 90 degrees. But you can also rotate by other by different number of degrees. Like so, for example, for 30 degrees, these are the numbers that you need. 45 degrees, you can do all sorts of things, right? So here's just rotation, here is scaling, rotation and scaling. And so this is how matrices work, and this is the effect that they have on vectors, on points in general, right? Okay, so the addition of matrices of equal size is just an element-wise operation. You just add the corresponding elements together. The scalar multiplication, again, is an element-wise operation, so you multiply each one of the elements by the scalar. And as we said, we apply matrices to vectors similarly to how we would apply a function to a vector, right? And we can also, by doing this application, we can also project or express, let's say, the vector in higher dimensional spaces. So it doesn't have to be the same number of dimensions, so we do that. Okay, so all application of a matrix to a vector does is form a weighted sum of the elements of the vector. So we weigh the elements of the vector by the matrix. Okay, so let's have a try. I think it's best if you say it through examples, right? So if you have this matrix A and you want to multiply to apply it, let's say to this vector x, you can actually have a couple of ways of doing it. So you have the traditional matrix multiplication approach, which is row by column, right? So I suppose you all know this, right? How that works, right? Presumably. You also have an alternative way of looking at it. Effectively, you're doing the same thing, but this is maybe closer to the idea of the linear transformation. But it doesn't really, I mean, it's just a matter of getting used to doing one or the other, and I'm used to doing the first way of calculating the multiplication. So how do we do that in NumPy and in Python? We can use this operator. We said last time that we can also use the NumPy norm function to do this between matrices, and we'll actually do matrix multiplication. Okay. Okay. So matrix multiplication then defines this product where A, B, and C are all matrices. And if A represents a linear transform and B represents a different linear transform G of X, then BAX is the G of F of X. So the second transformation gets applied first. I think as we do with function composition, I think it's pretty much the same. So the composition is read right to left. So to apply the transformation A then B, we need to form the product BA, right? So the one that's closer to the X gets applied first. Okay, so the multiplication algorithm that's how we describe it in math. But what's important to note is that if matrix A has P rows and Q columns, so it has a shape of P times Q, it can also, and B is Q times R, then the resulting product has dimensions P times R. And it's only defined if the number of columns of A is equal to the number of rows of B, right? So you have to have that so that it makes sense. Okay. Oops. And we also said that the order of multiplication is important. I think you saw that in the quiz as well. So that matrix multiplication does not commute. A times B is not equal usually to B times A, and you cannot make that assumption. You can, if you have the transpose of a product, then you have to switch the places of the matrices. And it's also true that you can actually have this operation here that holds, right? The transpose of the addition of two vectors is the same as the addition of the transposes of the vectors. Okay. So in general, the time complexity of the multiplication, if you want to calculate this, is of the order of P times Q times R, where P and Q are the rows and columns of the first matrix, and R are the number of columns of the second matrix. These are the numbers of, this is the number of comparisons that you do, the number of calculations that you do for you to do the multiplication. And if you multiply two square matrices, that is that all dimensions are the same, let's say n, then the complexity is O(n) cubed. For some special forms of matrices, for example, diagonal, triangular, sparse, and so on, this complexity can be reduced because you make different assumptions of the contents of the matrix. For general multiplication, the complexity is, even for accelerated algorithms, is larger than n squared, but usually less than n cubed. So you're usually in this n cubed territory, right, for general purpose multiplication. Okay, so this is the transposition. The transpose of a matrix, which is, we said that it's when we exchange the rows with the columns. How do we do that in NumPy? There are a couple of ways. One is this A dot T, and the other one is the NP dot transpose of A. So that will actually rotate the matrix for you. Okay. So we have a couple of, we talked about the dot product last time between vectors. And so the dot product is also called the inner product. It's when you do a certain operation between two vectors and you end up having a scalar as a result, right? A number. There is also the outer product, which is basically if you transpose the two matrices, you'll end up having another matrix as a result, right? So if I can write here. How does that work? It is okay. So, right. So if you have, for example, the matrix, no, that's too small. Right, so if you have the matrix A, B, C, D, no, rather you have A, B, and B, D. So let me just write it again. So we have two vectors. Let's say we have U and V. U equals A, B, and V equals C, D, right? Then, oops. Am I doing something wrong? Probably. Right. So, if you want to calculate the dot product, or one of the two products, how would you do it, right? So one case is that you have AB, well, if you do rows and columns, as we know that we do with matrices, you cannot just multiply like this, so you have to transpose one of them, right? So let's transpose V, which is then that we have C and D, right? So that multiplication there is equal to what? AC plus BD, right? Plus BD. So AC plus BD is a number, right? Is a scalar. So then basically what we do is that if we do U dot V is basically this, right? So we get this result. This is the dot product. This is the inner product. But if you change the transposition, you get this this outer product quantity, which is A, B, C, D, right? Which is AC, AD, BC, BD. Is that right? Yeah. So these are the two different matrix multiplications for vectors that we have. So we saw vectors as points in space and matrices as vector transformations. And then we talked about compositions, right? If we multiply different matrices together and then we apply them to a vector, then we have a composition of effects of linear transformations. Okay. So let's see what happens with the composition of these transformations. So here, for example, we have non-uniform scaling. So basically, we scale down one of the dimensions, and this is what we get, right? Or we can have rotation with no scaling. So this is scaling with no rotation. This is rotation with no scaling. Is that clear? And you can see it, right? This is the input, and this is the output. Yeah? Yes? And let's see what happens when we compose. That is the multiplication of matrices. So let's do, so this is the rotation and then scaling, right? So we scale x and then we rotate by 30 degrees. So if we rotate first and then scale, so you get the square and you rotate it and then you scale, well, you scale it non-uniformly. That means you squash it like this and you get this result. If you scale and then rotate, you get a different shape, a different resulting shape, right? Can you see that? Right, so it's a different shape. And this combination, this concatenation of transforms, this composition is something that we take advantage of when we want to do large operations. For example, in graphics processing. But you'll also, I think, see it in sort of larger vectors and larger matrices. In the case of neural networks, for example, that you have matrix multiplications in sequence. Okay. Okay. Now, before I go there, before I go any further, I would like to go a bit back and discuss a bit what it means to transpose this vector, right? The vectors. So what does it mean from the point of view of the coordinate systems that we are talking about? Because when a vector is, say, vector 3.2, this 3.2 is in a specific coordinate system, right? So 3.2 exists only in that vector space, and that coordinate system actually gets defined through the vector space. Okay. So if you have this, and you have, for example, 3, 4, 1, 2, 3, right? And you have the vector 3, 2 here, right? Then it's this 3, 2. The only reason why we say that it's 3, 2 is because of the vector space. Because if I take the axis away, then it doesn't mean anything, right? If I put a different set of axes, then it means something else. It gets some other number, right? So if, for example, I had, I don't know, some other system like this one, right? then this 3, 2 would be something else, right? Okay, does it make sense? It would, it would be some, I don't know, some 5, 1 or something in a different coordinate system, right? So let's see how and that's just the rotation. So let's just briefly see how this looks like. Okay, so you cannot see anything. It's not so great. But now you can, right? Yeah, okay. Okay, so here, can I zoom in a bit? No. Can you see at all? Okay, so anyway, I'll explain what's happening, right? So here I have the matrix, in this particular case, 2, 0, 1, 1, right? 2, 0, 1, 1. And you can actually do it by hand as well, right? So you can have 2, 0, 1, 1. And I'm multiplying this matrix with a vector. In this particular case, the vector 0, 1, right? And if I move this vector here, you see how it moves on the right-hand side, right? So this 2, 0, 1, 1, it kind of defines also that space. So if I have, say, a 0, 4 in this case, then it's also 0, 4 in this case, right? But if I have 4, 0, it becomes an 8, 4, right? And if I do the 1, 1, this square here is just a unit, just the unit of space. I mean, sometimes we call it the basis, or the 1, 1 vector is the vector, the 0, 1 and 1, 0 is the vector basis, right? At the end of the day, you see that if you see the geometry of this, of the resulting space, if I have a 2, 3 vector, which is this one, right? Can you see it, right? 2, 3 means basically I move 2 along the x-axis and 3 along the y-axis, right? So if I go here, I still move 2 along the new x-axis, right? 1, 2, and 1, 2, 3 above. So in the new coordinate system, the 2, 3 is still a 2, 3, but the whole system has actually shifted, has rotated, and has actually moved. Yeah? Can you see that? Right. So this is actually pretty important for you to understand. So this is the thing with the rotation and the scaling. You scale the vector gets scaled because somehow a new vector space gets defined. Right? So the space is important, and the properties of the space are important. And of course, you see here we have the, what was it, the 2, 0, 1, 1. So we have the 2, 0, 1, 1 matrix. And you can do it yourselves, right? So you have a coordinate system, which we know, and then what you want to do is that you want to somehow define this square, or some square anyway, right, for that matter. But this is the most kind of, probably the most useful. So this square is basically the 4 points 0, 0. So I'm transposing it now, right? Because I want to put multiple vectors into a new matrix, right? So 0, 1, 1, 0, and 1, 1, right? These are these 4 points that define this square. And if you do this, this multiplication here, effectively what you're doing is that you're applying this matrix to each one of those vectors, right? This is what you're doing here. And so here I would get 0 plus 0, which is 0, and 0 plus 0, which again is 0, and 2, and 2, again here, and so on, right? So you end up having this shape that I showed you. So you'll start by this square, and you end up having this shape here. Okay. And if you wanted to project this into 3 dimensions or 4 or 5, then what would you need to do? Basically, we said that the multiplication works. So if I have m rows and n columns here, then I need to have n rows and, I don't know, q columns here. And this m and q are the dimensionality of the resulting matrix, right? So this matrix will have m rows and q columns, right? M rows means 2 dimensions. So if this matrix was, say, 4-dimensional, 4 by 2, and this was the same, I would end up having a 4 by 4 matrix. That means 4 points in a 4-dimensional space. Okay? And everything else will be the same, right? Everything else holds, nothing changes, right? So it's just the transformation of a point from one vector space to another, where also the dimensionality changes. Okay, good. So I just wanted to show you this because I think it's important. Now, okay, so let's just introduce something at this stage that might seem a bit disconnected, but just bear with me for a bit. It's useful for you to see that. So let's talk a bit about the variance and the covariance of a data set or a sample or a vector, right, or a matrix. So the variance measures the spread of a data set. So if you have, for example, a bunch of numbers in a vector, what variance is the average distance from the average sample, right? So if if x bar is your mean, your average value, or your average vector, it doesn't really matter, your average something, then variance is really the average, right, of this distance of every sample from the average, this difference of every sample from the average. Is that clear at all? Right? So if you have, let's suppose you have a vector u, which is, I don't know, 1, 3, 4, and 7, right? Then what's the average of that? Is 8 plus 7, 15. The average, so is 7.5. Okay, that's the average. So then basically you take each one of those numbers, you find the difference, well, the square of the difference, right? So that's 6.5 squared, you know, so basically 1 minus 7.5 squared plus 3 minus 7.5 squared plus 4 minus 7.5 squared plus 7 minus 7.5 squared, right? And that's the variance. Okay, so this is the variance. It tells you how much the different numbers vary from the mean, from the average. So then you can actually extend this notion into the covariance. And the covariance between two data sets, two populations, is instead of having xi minus x bar squared, you have xi minus x bar, that is the difference, the distance from the mean of the first sample, times the distance of each one of the elements of the second sample from the mean of the second data set. Right, so what this does is that if covariance is larger than 0, yeah, okay, so then you average that, like by the number of the samples of the two vectors, the number of the elements of the vectors. So if covariance is larger than 0, then the variances coincide, right? So that means that if, as one sample increases, then so does the other, right? If it's less than 0, you obviously have the opposite effect. If it's 0, there is no linear relationship between x and y. So it basically tells us how the samples move in relation to one another if you have two data sets, two vectors, right? Something to note is that covariance is not standardized. Its magnitude is not bounded, right? So the numbers so it's not like between 0 and 1, right? It can take any values depending on what sort of values we have in x and y, okay? So this is the covariance. And based on the covariance, if you have multiple such variables, x1 to xn, you can calculate what we call the covariance matrix, right? And this is how this looks like. The main diagonal is the covariance of each one of the vectors with themselves. So that is basically the variance, right? And then you have all the other combinations calculated. And this is a symmetric matrix. That is that the upper sort of, the matrix sort of above the main diagonal is really a reflection of the part of the matrix below the main diagonal, right? And we say that something that's called eigenvalues are non-negative, which we'll actually talk about in a bit. Okay. So here you can actually see how to generate data samples and how to compute covariances using NumPy, and I'm pretty sure that you'll get to use that in your labs. And here you can actually, for a two data set, you have a mean vector 1 by 2 and a covariance matrix 2 by 2 because you have 2 dimensions, right? The mean vector captures the idea of the center, as we said last time as well, and you can also check it geometrically yourselves. You can actually draw it and see. And the covariance captures the spread of a collection of points in the vector space, right? So a large covariance will have the points more spread out, a smaller one will have them more concentrated, right? But of course, something else that you might notice here is that if you have this particular sample, these points, this sample of points, then you see that you have a lot of variance in this direction, maybe less variance in this direction. So maybe the axes that we have right now, they're not optimal, right? Just keep in mind and try to think about what we saw before, right? Okay, so some special matrix forms are the diagonal. Basically, the main diagonal are non-zeros, or not all of them anyway, and everything else is 0. Upper triangular means that the values above the main diagonal are non-zero. You have the lower triangular, which is the opposite. You have the identity matrix, which basically everything is 0 apart from the main diagonal, which is 1. We saw before that one of the properties of the identity matrix is that it doesn't transform anything. So if you have a matrix A times the identity, you'll still get A. You have 0 matrices and so on, right? And then also there is a notion of the matrix inversion, right? Inversion is defined such that the inverse of a matrix times the matrix will give you the identity matrix, right? So it's analogous to the inversion of the scalars. So for example, if you have the invert of a matrix A times X, that will give you X, because the invert of a matrix times A will give you the identity matrix. If you invert twice, you'll get A, right? And so on. Okay, so Inversion can be seen as an undo. So if the application of a matrix A results in a certain rotation and scaling of a vector, right? So you get the results. If you apply the invert of this matrix to this result, you should go back to the original vector. Okay. So if you do a 30-degree rotation, for example, here, you'll get the rotated vectors here, the rotated points. But if you do the inversion, you'll actually get the original set of points which you started with. Okay. Okay. So here, these are a few references for more reading if you want. And I think we'll probably take 5 minutes break. A 5-minute break, is that okay? Before we continue with the rest of the lecture. Okay. So maybe if you have things to ask me, you can, if you want to ask me, just come over and ask me. Hello.
Just want to ask first of all, I think the mean was not right on this calculation, right? Because you would take it for all the points.
So the mean was not right? Yeah, maybe.
So you take the average of all of these, right?
Yes.
So that would be like, or like calculator or something else.
So, okay, so...
It's like 15 by 4, right?
Yes, you're right. Yeah, you're right.
Okay.
Yeah.
And another question, you said if you take the inverse, it would kind of reverse the operation.
Yes.
But we also know like some of the matrices are not invertible. So what does that mean in a physical sense?
If the matrix is not invertible, then you cannot do that.
So that's an operation you can't reverse.
Yes.
But if it's like a rotation, you can just rotate it back.
Yeah. So usually we care about in matrices where the inverse is defined.
Hmm.
Right?
So you wouldn't carry out an operation like that in the first place.
You could give me an example of something that's non-invertible, and that makes sense to apply.
Yeah, so I can't think of anything like that in a physical way. Like if you're rotating, I'm assuming, I guess they will all be invertible.
Mm-hmm. The ones that we care about.
Yes. Yeah, okay. Okay, makes sense.
Yeah.
Thank you.
I just heard of the time the complexity we have seen, right? Like the terms PQR, and the n cube. Can you tell me the terms like what does the n represent and
What's the big O?
like
What is the complexity?
yeah.
Do you know what the complexity is?
Yeah, I know the complexity. Right. Like the terms, like what does the n represent, like the n and the other terms like PQ.
PQ and R. So
What is
yeah. So PQ and R is that if you have a matrix A that is basically if A is say P times Q, right? So it has P rows and Q columns, and B has Q rows and R columns.
okay?
Then the complexity of their multiplication
Okay.
is PQR. Is that.
Okay. The n cube.
If the right, so this is assuming that PQ and R are different numbers.
Okay.
Right? If you have square matrices,
Okay.
then by definition you would have, say, the first matrix being something like n times n,
Yeah.
right? And the second one should be also n times n, because otherwise you wouldn't be able to do the right. So in that case, P equals Q equals R equals n.
Oh yeah.
So that's why you have
okay.
n
Okay.
cubed,
Okay. Yeah.
right?
Hello.
Yes. Oh. Did I do it the wrong way around? AC. Yes, you're right. Yeah, I did the wrong way around. Oops.
Yeah, so basically, effectively, this, yeah, this, yeah. Okay, well, for the, yeah, that was my mistake. So that was wrong, right?
Yeah, it's 3 points.
3 point something.
Yeah,
25.
3.25.
Right, 3.25. Okay. So 3.25. Yeah, no, I divided by 2 mistakenly, right? So then basically the variance is the average, distance of each one of the points from the mean. Right, so if you have a concentrated sample, these distances are small, so the average is small. If you have a spread out kind of sample, then set, then you have a bigger variance. Yep. Yes. That's because I did this wrongly. We have the wrong way around. Sorry about that.
It's a simple. We still not understand the law.
Yeah, I can. It's just did it the wrong way around. Right. So the right. So this would be. Yes, exactly. Yeah. Yeah.
That's the inner product.
Yes, that's right. Yeah. This is the wrong way around. But most of people didn't notice. But I'll explain it now.
Okay, so let's continue now. So some of you noticed that I made a few mistakes. Actually, pretty much everything that I wrote on a piece of paper, it was wrong, right? So, but especially in this case, with the outer and the inner products, it was the other way around, right? So many of you spotted it correctly. Okay. So this here is the outer is the outer product. So let me just write it. So if I have U outer product V, that would be A, B, C, D, which results in AC, AD, BC, BD. Is that correct now? Yeah, probably. And the inner product would be AB. Okay. Is that correct now? Can anyone who came to speak to me verify? Okay. So that was one mistake. The other mistake, of course, was that the average here is 3.25 because I divided by 2 and not by 4, right? So we'll spell that. But the principle is the same, right? It's exactly the same. So the variance is the average distance from the mean is the average distance of all points from the mean. Okay. Okay. So so let's continue. So do you have any questions before we go any further? Any other questions? Okay, so now we'll talk a bit about graphs as matrices. Let's suppose you have a number of warehouses that have different products, and what they do is that they need to distribute, what they do is they distribute packages, so they move packages from one warehouse to the other. And you have a certain connectivity between the different warehouses, so that not all warehouses are reachable from all other warehouses, right? So one objective here is to, for example, to predict which warehouses are going to receive lots of packages or more packages or fewer packages and so on, right? So how can we model this problem? We can actually draw a graph, right? And this is a graph. And let's suppose, for example, that you have a bunch of warehouses, A to H, right? And the arrows and, well, the lines between them indicate paths where packages can actually travel. And what we assume is that packages arriving at one site is a weighted sum of, can be expressed as a weighted sum of the packages currently at each other of the other side, so that you have you cannot have packages arriving at any one site that are completely disconnected to what the capacity of the other warehouses is, basically, right? So we might choose to model this as a graph. So this is a directed graph which connects vertices by edges. So vertices are your nodes, your warehouses, and edges are the paths between the warehouses. So we define this graph as so. That's the graph G, is basically a set of vertices and a set of edges, V and E. And we say that this is a directed graph because we can only travel one way, and this is why we have the arrows, right? So if it wasn't a directed graph, we wouldn't need the arrows, right? So we can write this as an adjacency matrix. How do we do that? So we label each vertex 0, 1, 2, 3, and so on, so that we end up having vertex 1, vertex 2, and so on, right? And we create this square matrix, we call it A, whose elements are all 0 except where there is an edge from Vi to Vj, right? And in this case, we set Aij equal to 1. Okay. And you will notice here that the main diagonal is zeros, because in this particular graph, we don't have paths from a warehouse back to itself, right? Maybe you have that case in other examples. Okay. So the way that we've modeled it here is that the out degree of each vertex, that is how many numbers, how many edges leave a vertex, right? Say, for example, from A, you have 3 outgoing edges, 3 outgoing paths, right? So the out degree, this is the out degree. The out degree of each vertex is the sum of each row, okay? So for A, for example, is 1 plus 1 plus 1 is 3, right? For C is 2, 1 and 2, right? Because you have 2 outgoing edges. The in degree of each vertex, which is the opposite, is the sum of each column. If the matrix is symmetric, that is that the elements of the above the main diagonal are really a reflection of the elements below the main diagonal, then we say that the graph is really undirected, right? Because if you can get from A to B, you can also get from B to A, right? So you don't need the arrow, effectively, right? And you can convert this directed graph into an undirected graph by computing by making that computation, right? So the new matrix is equal to A plus A transpose. Okay. And if there are non-zero elements on the diagonal, that means there are edges connecting the vertices to themselves. Okay. Now let's suppose, so now here, in this case, whenever there's a path from A to B, and from C, they're all equivalent, right? They can carry the same number of packages or whatever, right? We can actually make them, make some of the connections stronger or more efficient, or whatever it is that you're modeling, really. It doesn't really matter. So in this particular case, we can assume that if, for example, they are connected by bigger roads, maybe we give them a bigger value. Yeah. So now the entry at Aij, at each part of the adjacency matrix, represents the weight of the connection. Okay, so so effectively, the graphs now represent kind of flows of mass. We say some sort of transfer of some quantity from one to the other at different volumes or different capacities or different bandwidths. So if the total flow of a vertex is greater than 1, that is, its row sum to larger than 1, then it's a source of mass. For example, it's manufacturing things, so it has more things going out than coming in. Right? If the total flow is less than 1, then it's a sink. It receives more things that it sends out. Okay. If it's exactly 1, then it conserves mass. Okay, so it just reroutes things, so it doesn't do anything else. So then, how do we use this abstraction to predict which warehouses are going to receive more packages than others? So because we have the linear assumption, all the packages arriving at one site is the weighted sum of the packages currently at other sites. And so we can actually, at any point in time, we can write down the proportion of packages at each depot, at each warehouse, as a vector, where phi is the number of vertices in the graph, the number of warehouses. So let's suppose we give it some values. Then the flow of packages per day is this linear map. So we use the adjacency matrix as this linear map. And then we can apply this linear map to this vector that is the proportion of packages and see what comes back, right? So if we start with an initial distribution of packages like the one we had, then we need to apply this transformation every day, repeatedly, to actually see how will this distribution change day by day, right? So what this allows us to do is that it allows us to analyze a discrete problem, which is, say, the connectivity of graphs with tools from continuous mathematics, such as vectors and matrices. So that's powerful, right? Okay, so you can actually have a look at this later, but then the thing is that if we apply it once, we'll get some results. Okay, but what happens how about in a week's time, or how about in an hour's time, if we have 24 hours per day, or whatever it is, so the way that we model time. What about an infinity kind of time? What's the long-term behavior? Will the system reach a steady state, or will it just keep on oscillating and changing the distribution of the packages? And what if we wanted to go backwards? So similar to the warehouses, we can actually model a number of problems. A very famous one, I suppose, is the web, right? So users moving between web pages, or the way that web pages connect to other web pages. There we have the notions of and the concepts of inlinks and outlinks pretty explicit, and also it's pretty easy for us to understand that if you have a website, and it's pretty basic, a website, for example, with many outlinks, then it acts as a, let's say, a manufacturer or a hub, so it carries traffic to multiple different players. If it has a lot of many inlinks, then it's a kind of it's probably an important resource, so we need to pay attention to it. But we also have trade between states. We have a number of different problems that can be modeled through adjacency, through graphs and through adjacency matrices. Okay, so we said also that we can actually, since we can multiply matrices, we can multiply a matrix by itself many times, right? So you can have A squared, that's A times A to the third, to the fourth, and so on and so forth. And we also said that matrices can be inverted, the ones that can be inverted. And this, in effect, undoes the effect of a matrix transformation, of the original transformation of the matrix. What else can we do? We can find eigenvalues which identify specific vectors that are only scaled by matrices, so they're not rotated. So they change very basically, right? And we can also factorize matrices. We can express a matrix as a product of multiple other matrices, and so on and so forth, right? So now that we can define this exponentiation, A squared, A to the third, and so on, right? How can we model this week's time prediction? What will it be, our estimation of this distribution at t equals 7, right? For example. We can simply ask the matrix 7 times. So we can raise it to the power 7 and see what comes back, okay? And as usual, you can do that in NumPy, and you can have a look, right? So if we apply this multiplication multiple times, this is what happens, right? So if that's the original, then you have a 7-degree rotation. If you multiply it by A once and then again another 7 degrees and another 7 degrees and so on, right? So imagine that you have this conserving agency matrix, adjacency matrix, modeling the flow of packages around a network of depots, right? So these are the adjacency matrix as we had before, right? So let's suppose that we have an initial distribution, package distribution, and then we start doing this experiment by having these exponents of the adjacency matrix. Let's see what happens. So if we run this experiment a few times with 5 different starting states, you see that at the end, we end up having the same thing. So the system reaches an equilibrium. Okay? And that might be a bit surprising. But the thing is that because you have a steady flow inside your system, after a few iterations, you're bound to have a steady the same result. So what happens here is that after multiple times that we've actually multiplied this matrix, this adjacency matrix by itself, we end up not having any rotations anymore, basically, right? And we say that this vector is one of the eigenvectors of the adjacency matrix. One of the basic vectors that describe this adjacency matrix, right? Applying the matrix again does not change the distribution of the packages anymore, right? So what is then an eigenvector and an eigenvalue? So we said that the matrix, we said many times, represents really a transformation, right? A linear transformation. That means a rotation and a scaling of vectors. Okay? But there are certain vectors which will not get rotated, will multiplied by a matrix. They only get scaled. These vectors are called the eigenvectors, and they can be thought of as the fundamental or the characteristic vectors of the matrix. The scaling factors applies to these eigenvectors, the scaling factors that the matrix applies are called the eigenvalues. So the scaling is the eigenvalues, and the vectors that cannot be rotated are the fundamental ones, are the eigenvectors. And now what other vectors can we think of that cannot really, rotation doesn't really apply, transformation like this doesn't really apply? Let's see. So this is another example of how this looks like, how we can visualize this. If the edges of this shape are the eigenvectors of the matrix, this will only be stretched or compressed. It will not be rotated. If the eigenvalue is greater than 1, then the eigenvector is stretched. If it's between 0 and 1, it's shrunk. Okay, so that reminds us of something. If the edges of this I don't know how you pronounce this, have unit length, if anyone knows, you can tell me, then after the transformation, their lengths will be equal to the eigenvalues. Okay. So how do we find the leading eigenvector? This is the power iteration method, and it's none other than the one that we described before. So we basically take the exponentiation of a matrix multiple times. We apply the matrix repeatedly to a random initial vector and wait until the result converges to a steady state, right? If we do it naively like this, then this will generally either explode, it will get a really huge value, or it will actually collapse to 0 because of the repeated application of the multiplication, okay? But we can fix this by normalizing the vector after each application, right? So we basically do a squared, we normalize. A cubed, we normalize, right? By dividing by some norm, right? Here's the infinite norm. And this process is called power iteration, and it allows us to fairly efficiently calculate the first eigenvector. So regardless of which vector we start with, we are kind of guaranteed to end up with an eigenvector at the end. This is true for almost every square matrix. The vector that results is known as the leading eigenvector, is the most important one, the most characteristic one of the matrix that we start with. It satisfies the definition of an eigenvector because the matrix A performs only scaling, so it doesn't rotate anymore. The scaling effect is eliminated by the normalization step, but any other effects pass through. And this is what we write. We can write the scaling effect of A on an eigenvector as follows. So this is a pretty standard notation, and it describes exactly what the eigenvector and the eigenvalue is. So that when you apply A to X, a matrix A to a vector X, this is equal to a scalar multiplication of that vector by some scalar lambda, right? And here lambda, it only does the scaling, and it's called the eigenvalue, okay? So if we want to know all the eigenvectors, so if we do this power step, this power iteration, will actually lead very quickly to the leading eigenvector. But if we want to know all the eigenvectors, then we have to use this method here from NumPy. Or of course, I mean, if we have a small vector, we can calculate it by hand. And we might see an example next week. For large matrices, what is interesting is that if you only want the leading eigenvector, it's much faster to do it through power iteration than through the NumPy function. So we said that then you have a vector function. It's the same as having the application of a matrix, right? So you have this f of x equals lambda x, right? So the function maps these vectors x to scaled versions of themselves, right? So it doesn't rotate them, it just stretches them, right? So there is no rotation or skewing, just scaling, right? So you just enlarge them or make them smaller. So any square matrix that represents this function may have vectors like this, so that this holds, right? This is true. Each vector xi satisfying this equation is known as an eigenvector, and each corresponding factor, lambda I, is known as an eigenvalue. For any matrix, the eigenvalues are uniquely determined, but the eigenvectors are not uniquely determined. And they're not uniquely determined because we only care about their direction. Right? So you might have like different lengths, so that means different vectors, but the direction is the same. The eigenvectors are orthogonal, right? So they are perpendicular to one another. That means that their dot product will be 0, right? Okay. Effectively, they define a new coordinate system in which the transformation A becomes diagonal, and we'll see that in the factorization part, meaning that it only stretches or compresses along these axes, right? Okay, so it's basically, you can think about it as a new alternative coordinate system. Okay, so then based on the eigenvectors and the eigenvalues are pretty fundamental for a number of solutions in linear algebra and machine learning and what have you, engineering, whatever. And this is exactly what happened with our package distribution problem, right? At some point, the long-term behavior will come to an equilibrium, right? Okay, so here we have some examples, an example of how to actually calculate those things, right? So first of all, if we go back to the adjacency matrix example with the warehouses and the graph, so first we make the adjacency matrix symmetric, right? So that we don't have to worry about transposing it before we apply this eigenvector calculation function, right? You can see that it's symmetric, right? And then we compute the eigen decomposition of A. We effectively express this matrix through its eigenvectors. So that we know that different parts of this eigen decomposition will do more specific things. They will not do both rotation and scaling. They will, so we have a much more controlled solution. So this is how you do this. The leading eigenvector tells us what the steady state of the package distribution will be if we keep the system running for long enough. Small eigenvalues correspond to root patterns that are rarely used, right? And large eigenvalues correspond to dominant paths. So you remember that our edges have numbers, right? And for this distribution network, most of the packages then will pile up at A, B, C, D, and H. Okay. Now, we said that we have multiple eigenvalues, and so then we can actually sort them. And the eigenspectrum is the sequence of absolute eigenvalues ordered by magnitude. The ranks of the eigenvector, this ranks the eigenvectors in order of importance. Each eigenvector is orthogonal to one another, but it has a sort of an order of importance. So this can be useful in finding simplified versions of linear transforms. This is again very crucial, right? So that tells us that we can find, we can transform an initial data set in a new set of axes where different, well, not all axes are equally important to in describing that data set effectively, right? Okay, that's about numerical instabilities in NumPy and elsewhere, and you can use this Hermitian matrix to overcome those. And now I would like us to start talking a bit about principal component analysis. So we talked about the transformation that matrices do. I showed you how rotating and scaling a vector can actually give us an indication of a new space, a new vector space, and how this might look like. We said that we can actually move between different dimensionalities of vectors. Then we talked about the eigenvalues, which are a special type of coordinate system for our data set. We talked about the variance and the covariance, and the covariance matrix. So now let's see how we can actually, how can we use this for an actual data science problem, which is how can we analyze data or a multidimensional data set using that. Okay. So the principal component analysis is a very basic algorithm in data science, I suppose, in general, in statistics. And it involves identifying the principal components of a data set, right? And what are those principal components? We'll see. Okay, so let's generate a data set in a two-dimensional space. And let's suppose that these are the first 10 observations, right? And so we plot them like this. We've talked about the mean vector, which is the geometric centroid of the set of vectors that this data set consists of. And we can think about it as capturing the center of mass of those vectors. And then we talked about the covariance matrix, even though we kind of defined it slightly differently, but they are equivalent. Which is basically, what is it, the covariance matrix? It's a matrix that defines how the relationship in variance between the different elements of a data set, different dimensions of a data set. Okay? All combinations between the vectors of a data set between themselves. So if right, is that clear at all? Shall I show the other slide? But what you need to remember, though, about the covariance matrix is that it's a square matrix, and it measures the spread of a data set. So and not just the spread, but also the shape, right? So how do we do PCA? First of all, this is an optional step. We can standardize the data. So we scale them so that they have a mean of 0 and a standard deviation of 1. The standard deviation is the square root of the variance, right? Then we compute the covariance matrix. We perform eigendecomposition, that is, we find out about the eigenvalues and the eigenvectors of the covariance matrix. So now we know. So now the eigenvalues, the eigenvectors of the covariance matrix are these principal components, right? They are the principal components that describe the variance of this data set. Okay? Then we sort the eigenvalues in descending order, because we said that the larger the eigenvalue, the more important the corresponding vector, right? And we choose the top k eigenvectors, where k is the number of dimensions we want to keep, right? So here, for example, we start with 2 dimensions, right? And then we transform the original data using these key eigenvectors to get the principal components. Okay. Now here, the eigenvectors, the principal components, they tell us the directions in which the data varies the most, right? So this data set, the way that it's shaped, it mostly varies along this orange axis, right? You can see that, right? So it kind of goes like it's elongated along this axis, and this is the first principal component, right? And then all the other eigenvectors will be orthogonal to this first one. They are really a system of a coordinate system. And so the second one is the second most important. The third one, here we only have 2, right? But you can have multiple dimensions. Let me just find something, right. So what we are effectively doing here is that we are, so here we have those 2 principal components. But then what we want is we want to map all the data set, all the data points onto one of those principal components in this particular case, right? So we'll choose the most important one, right? The first one, which is this one, right? And then we can actually map each and every one of those along this new axis, right? And so what we've done there is we've lost some information from the second coordinate, the second axis, right? But we've retained most of the variance in this particular case, right? Because it's really elongated. So now we are reconstructing the covariance using the eigenvectors and values. I think I would like to explain those better next time. What I would like to see, to show you though, is this, right? So we have the original data points in 2 dimensions. We discover this eigenvector, which was the first principal component, which went like this, right? And then we project each one of these points onto this axis, right? This component, and this is what we get, right? Effectively. So what we managed to do, we started with 2 dimensions, and we ended up with 1 dimension that preserves most of the structure of the data set, right? Imagine starting with thousands of dimensions and ending up that maybe 5 or 6 or 10 are enough, right? So, uses of eigen decomposition. So first of all, okay, matrix decomposition in EGPCA is very crucial, and we use it a lot. It's been used in recommender systems, image compression, visualization, and so on. So you can imagine that if you have, say, visualization, right? So you do your really nice experiment using, I don't know, tens of thousands of vectors, and somehow you have to, you want to show it to somebody, right? So that means you have to reduce dimensions to 2, right? Spectral clustering for graph-based clustering. The PageRank algorithm, that's the infamous Google algorithm that determines the relative importance of web pages. Latent semantic analysis, which is a text mining technique for topic modeling. This one uses something that's called singular value decomposition, which is a generalization of eigen decomposition, and we'll see next time. Okay, so I think that I would like to stop now, actually, because matrix inversions we said because I would like us to have more time to go through eigen decomposition and follow this up with more examples next time. Okay, so are there any questions? No, so everything is clear. So, so I think that the second quiz must be up by now, right? That's due tomorrow. So have a look at it, have a go at it, and I'll see you, I suppose, next week. Right? If you have any questions that you want to ask me, you can obviously come. Thank you.
So can you explain the eigenspectrum?
The eigenspectrum
Yeah.
is basically the listing of the eigenvalues in order of magnitude. So you get the most important eigenvalues that
Okay,
you
like in a
basically sort
sorted.
them. Yeah.
Okay.
Yeah, you sort them because that tells you um, which eigenvector is the more important.
Okay.
Because each eigenvector corresponds to each eigenvalue.
Yeah.
So that's the eigenspectrum.
Can you explain this whole spectral clustering?
Yeah, no. No. Spectral clustering is an algorithm method, is a data science method for clustering. But this is not something we can actually do now yet. But you can have a look at scikit-learn. Do you know scikit-learn? sklearn? Okay, so sklearn is one of the important Python packages for data science. And, right? sklearn, right? And sklearn has really nice documentation. So if you go under clustering, you'll find all sorts of different types of clustering. Ah, hi.
Wanted to know, I'm an international student, MSc.
Sorry?
I'm an international student, MSc.
Okay.
Yeah, I
Is
wanted
MSc Data Science?
the MSc data science. Yeah. I mean, last week quiz. I wanted to know if there is quiz last week.
This is fine because the quizzes, the way that so first of all, the quizzes we do them mostly for engagement, so that people kind of engage with the material. Right? The other thing is that there's going to be about 10 quizzes, and we'll take the best 7 of them. So you don't. So let's do the other one.
Yeah,
Right.
okay. Thank you very much.
Okay. I don't think I've uploaded them
Okay.
yet.
It'll be in week 2?
In week 2.
2, okay.
Week 2. Week 3 is next week.
Yeah.
So I was wondering if you could be given some sort of like problem sets or something to practice because I was looking at the past papers, right? It's like, okay, I understand the theory, but it's a bit hard to study from the slides and then go straight into the final exam and have the questions. Like, if you could refer a book or something, I'm not sure.
Yeah, there are a couple of books that have been.
But it's like this isn't a linear algebra course, right? That I could pick up the linear algebra book and study. It's like a mashup of everything. So like it'd be great if there were some, I don't know, problem sets or something like that. Because for the lab we have the lab 0 lab exercises, but for the theory side there's not really much to
Yeah.
actively engage with.
Yeah, so each part of the course will have its corresponding books and resources, so you can read those. And there's actually a pretty good book that's been suggested for the linear algebra one.
Yeah, the Gilbert-Strang one, right?
Yeah, so that's the linear algebra part, right? Obviously, you'll have the other parts, the probability part and the optimization and the data.
So I'll just like identify the topics and practice from.
Well, the topics are pretty standard, right?
Yeah,
I mean,
that's true.
okay. So, but next week, that's what I mentioned last week as well, and I mentioned it today as well.
Yeah, there will be like an assignment or something.
It's not going to be an assignment. There's going to be I'm going to send you a couple of questions or 2 or 3 questions or something, which are going to be exam style, let's say, right? And what I would like to do ideally is that you come here with pen and paper, and we go through these questions and then we
Like in
solve them
class.
together, right?
Okay.
Because I understand that there's this discrepancy between this material and what you're
Right,
asked in the exam, right? So we'll do that next week. I'm hoping to send you something on Monday. If not Monday, then Tuesday, so that you have a couple of days before
Right.
our next lecture, and then we can actually. But yeah,
That would be great. Thank you.
Yeah.
So actually I needed so nobody added me to the Microsoft Teams.
you're not on Microsoft Teams. Okay, so since we have some time, let me just add you now.
So,
But you have access to Moodle, right?
yes.
Yeah, okay.
And also, sir, our students were unable to give the quiz with solving quizzes.
Oh, that's fine. That's fine.
Like
Yeah,
the quiz don't have a grading.
yeah, they have.
Yeah.
So you won't get a grade. No, I mean, yeah, that's true. You want to get a grade, but the grade. So the reason we do the quizzes is basically for you to engage with the material, and that's why they get marked a very small part of your grade. But also we take into account the best 7 out of 10 that you do, right? So you have like 9 more quizzes, right? So you should be fine, right? If you could tell me your email, your university email.
Sorry, sir. C1.
Three one
Your
some-
ID card has. I don't have. So, like, we will be providing the questions beforehand the lecture, and we will be
What questions?
like.
Could you maybe tell me the 31?
So 3171
7
1
1
086.
086. So that's
Yeah.
Kirti, right?
Yes.
Okay. You should be fine. Yeah, did you get it already?
So, like you were telling that in the lecture we will be solving the questions.
Yes.
So that question you will be giving beforehand so that we
I'll
can.
send you, yeah, yeah. So I'll send you a couple of questions or 2, 3 questions that are the style of the exam. So in the exam, you won't have the same questions, obviously, and maybe you won't have the same style, 100%, right? But just so that you have some practice with the more theoretical aspect. And that's why I asked you to just, we'll do it on with pen and paper.
Okay.
So no NumPy, no nothing.
Okay.
Okay?
Can I ask to the slides? These slides will open.
Yeah, I'll upload them later.
So,
Yeah.
do you mind share the slide before the lecture day? So
Yeah, I kind of do because I usually don't have time to prepare them.
okay. Yeah,
100%, right?
I saw today the it's different with the last week. You added maybe two slides.
I'm gonna update. I'm going to update these slides for you, right?
Yeah, because I think for myself, I really want to preview the slide before so I can understand more, get more things on in the
I wish
lecture.
you all the best.
Yeah, yeah.
I'll do what I can.
Okay. Cheers.
Okay. But
Thank you.
but usually, but you know, I mean the reason why this is the case now is because I am also kind of, this is the first year that I'm doing this.
Oh, yeah,
So
okay,
I'm
okay.
kind of working on the slides and trying to understand also the kind of the storyline of the slides because I haven't written them. So I'm trying to kind of understand how they work. That's why I cannot upload them before because
that's the reason.
I also
Yeah,
need to study them. Right.
It's your first year. That's really,
yeah, so,
that's okay. It's okay.
yeah, so-
if
so
you
that's
can
it.
share a little bit
Oh
earlier,
yeah.
that's really helpful.
I'm gonna upload everything, and also whenever I make changes, I then will be updating the slides, right?
Yes, thank you.
Because,
I thought today you
but
have
yeah, I mean,
two more slides.
because ideally, yeah, these are more for your like for you to understand better the material.
Yeah,
They are not really crucial. I haven't really changed anything in the in the course or in the exam questions and so on. It's just that to my opinion, some things could be a bit made to be a bit more understandable, a bit more comprehensible. So that's why I'm trying to help with.
Yeah, I have another question. So there's a 10 vector in an array. So this is a only this is an array or this is a matrix. So when we write down this kind of array, we might be to write down 2 arrays. Maybe I don't
So
know.
which are we? Give me an example, maybe. There you go.
So it's a, do we need to like give both quiz and assignment or just?
What's the
Do
question?
we have like both quiz and assignment, or else we have to do only quiz?
No, you have the quizzes, so that will count towards, I think, 6% altogether. All the quizzes.
All the 10 quizzes.
All the, yeah, the best 7 of the 10 will count towards, I think, 6%, if I remember correctly. Then you have 3 lab assignments for 8 points each, 8 grades, so that's 24 altogether, right? And then you have 70% of the mark through the written exam,
Theory, okay.
right? It's in the Moodle. It's on Moodle. Yeah.
Thank you.
Okay.
I have a question. These are some the 6 vector in this one. I think I don't know what it is. I know this is the 2 or 3 multiple 2 matrix.
That's 2 by 3.
Oh, 2 by 3. Okay.
So the first number is the number of rows usually.
First number.
The first number is the number of rows.
Okay.
And the second number is usually the number of columns, right?
Okay.
So it's 2 by 3.
Yeah, 2 by 3. And this one is only, this is an array, this is a matrix.
So in this context, we have matrices and we have vectors.
So
So
only vectors, like it's only a number.
so an array is an array is really an array of numbers, a sequence of numbers, and it's a programmatic artifact.
Yeah,
So
the array is actually in the program.
Right.
We can have the array.
So in programming, we have arrays of numbers because in memory, you put them in a sequence.
Yeah.
Right.
Okay.
So that's the only reason. But in mathematics, you don't have arrays.
Uh-oh.
You have vectors and you have matrices.
Yeah.
So this, strictly speaking, if you have, I mean, it's all the same. I mean, really, I mean, for what we do here, it doesn't make any difference, right? But if you have this, I would say that this is probably a 1 by 6 matrix, I would call it. Or maybe you could say that this is, so if this is a, the vector, say, would be, say, x, would probably be written like this.
Yeah, 6
right?
by 1.
Yeah, exactly, yeah. So, but these are subtle differences. They don't really make much difference in practice, because here you would have 2, 3, 6, 9, 10, whatever, 11, right? And you could also have the X transpose, which would be this.
Yeah.
Right.
Yeah.
So it doesn't really, but strictly speaking, usually when we talk about vectors, we have them like this, right? So usually, right?
Like the vector, like the object in program.
The vector as in math, right?
Yeah, in math.
Right.
Yeah.
So yeah, I mean,
the programming thinking to understand this kind of things.
I mean, in programming, I mean, if you think about it, the vector and the matrix is really an array.
For me, I think I probably will think about it's a object. It's an object. An object with different inside is different, but the whole things like this one, the whole things is a vector.
What's an object?
Object.
Why are you bringing objects into this? Don't think about objects.
Because I'm a programmer before, so I learned the programming. So
good. But however, they're not objects. They are arrays.
Okay.
They are right.
Yeah, for structure.
The object. The object, you can call it an object if you attach methods to it.
Yeah.
And you make it object-oriented, but that's irrelevant. It doesn't really matter. So what you want is that in programming, these are arrays.
Yeah, definitely.
And not only are they arrays, but they are all one-dimensional arrays. It doesn't matter if you have 2 dimensions in NumPy. In memory, you have a single, right, thing.
Yeah,
right. So that's why what I'm trying to say is that think about them on a higher level. These are vectors, and vectors, if you have one, one by something or something by one.
I can understand.
This is really a vector.
This the whole thing can be a vector.
Right, and
one
this
number
is
also can be a
and
vector.
this is a matrix.
Matrix, yeah.
You can also, in the literature, you might also find multidimensional, like multidimensional vectors, and you can say, okay, this is also a vector that is 2 by 3, whatever. It doesn't really matter, right? So what matters is that you know that this is a vector, this is an array, and what also matters is what you can do with them and what they mean.
Mm-hmm.
The programming is a different thing.
Yeah, programming is different.
It's different
Yeah,
thing.
yeah,
So
yeah, yeah.
in programming, you can rely on going np dot array blah blah blah, and you give it, and then you give it an A, and then you do this B, and then does matrix multiplication, and you're happy.
Mhm.
That's fine, right?
Thank you.
Yeah.
I can
So
understand.
don't mix the two.
Yeah,
This is
I can understand it. This is a vector. It's
yeah,
not
yeah. I would call that a vector.
Yeah. Thank you.
Okay, no worries.
let's just use confused.com. What if